Hi students, welcome to my channel Learning with Sarita. Today in this session we are going to discuss the topic electric field due to continuous charge distribution. As the first part of this session, we will learn what is continuous charge distribution. From the name itself, we are able to understand that the charges are spread continuously. And two, the charges are closely bound together and the individual charges cannot be looked at in the continuous charge distribution. Likewise, we can count the charges in discrete charge distribution Q1, Q2 and so on up to Qn. But in the case of continuous charge distribution, the charges are closely bound together and the individual charges cannot be looked at. And for continuous charge distribution, to find the electric field at the point, we are using the method of calculus. Calculus methods are nothing but we use the integration methods to find the electric field in the case of continuous charge distribution. Now we consider an irregular object. The charges will be continuous and the charges will be closely bound together. Can we count the charges Q1, Q2 and so on up to Qn in continuous charge distribution? No. So what we have to do is we are going to divide the whole body into charge elements. Charge elements like del Q1, del Q2 and so on up to del Qn. See here the picture. We are dividing the charges into the charge elements and randomly I have selected del Q1, del Q2, del Q3 and so on up to del Q1. Instead of point charges, here charge elements are to be considered. In the case of discrete charge distribution, we use the word point charge, but for continuous charge distribution, we are supposed to use the word only charge elements. We should be very careful in writing the continuous charge distribution. Under the continuous charge distribution topic, we have to use the word charge elements. Okay, students? Now, as the second part of this video, we are going to represent the electric field in terms of integration. Here del Q1, del Q2, del Q3 are the charge elements and the field that are created will be del E1 vector, del E2 vector, del E3 vector. Here we consider the diagram, a continuous charge distribution with charge elements del Q1, del Q2 and so on up to del Qn. And here the point P is taken. The field created due to del Q1 is del E1 vector. The field created due to del Q2 is del E2 vector and the field due to del Q3 is del E3 vector. Now what will be the electric field at the point P? We know that it is the sum of the fields created, isn't it? But particularly here in continuous charge distribution, we have to say sum of the fields at P is due to all the charge elements. Okay, you have to use this word charge elements. Now we are going to give the expression for E vector. It is equal to 1 by 4 pi epsilon naught del E1 by R del Q1 by R1p square R1p unit plus del Q2 by R2p square R2p unit plus and so on. And since we are adding the terms, I am introducing the summation. So E vector is equal to 1 by 4 pi epsilon naught summation I is equal to 1 to n del Qi by Rip square Rip unit. And we know that del Qi is equal to the ith charge element and Rip is the distance of point P from the ith charge element and Rip unit is the unit vector pointing from ith charge element towards the point P. Here for continuous charge distribution, when we take for limit del Q will be tending to 0. Here tends to 0 is not acceptable here, because we need some minimum value of charge, isn't it? That is, some infinitesimal value of charge must exist. Infinitesimal means it is not zero, just a minimum value. Okay, so we have to replace del q by dq, and we are replacing summation by integration. Now what will be the expression for E vector? 1 by 4 pi epsilon naught integral dq by r square r unit. Here r is the distance of p from the infinitesimal charge dq, and r unit is the unit vector from dq pointing towards p. Okay students, if the test charge which is at the point p is q, what will be the force experienced by the test charge? It is given by F vector is equal to q E vector. Now the third part of the session is types of continuous charge distribution. There are three types of continuous charge distribution. First one is linear charge distribution, second surface charge distribution, and third volume charge distribution. First, let's see about linear charge distribution. From the name itself, it's very clear that the charges are distributed along a line. If we consider a wire or a long thin rod, how the charges will be arranged? It will be arranged linearly. Now we are going to define linear charge density. What is it? Linear charge density is defined as the quantity of charge per unit length. For a unit length, how much charge is there? Now the linear charge density variable is lambda, that is equal to Q by L. Q is equal to uniformly distributed charge in coulomb, and L is the length of the wire in meter. The SI unit of linear charge density can be given by coulomb per meter or C m power minus 1. Here students, you consider the diagram. Here the length L is split into infinitesimal values dl, and we are going to consider an infinitesimal charge dq. dq here, then this dq is considered to be at a distance of r from the point P, and the r unit is the unit vector pointing the direction from dq to P. That is infinitesimal charge in infinitesimal length. Now the electric field E vector due to the line of total charge Q is given by E vector is equal to 1 by 4 pi epsilon naught integral lambda dl by r square r unit. Here lambda is constant, so we are taking it outside. E vector is equal to lambda by 4 pi epsilon naught integral dl by r square r unit. Here r is the distance between infinitesimal charge dq and the point P, and r unit is the distance from dq towards P. Second is surface charge distribution. Here the charge distribution is over a surface of the object. We are considering a metal sheet, and the surface charge density is defined as the quantity of charge per unit area. And the variable which is used for surface charge density is sigma. Sigma is equal to Q by A, where Q is the uniformly distributed charge in coulomb and A is the area of the sheet in meter square. And the SI unit of surface charge density is C m power minus 2. Here we consider the diagram of the metal sheet, and we are taking a charge element dq, and the point P is at a distance of r from the charge element infinitesimal charge dq, and r unit is pointing the direction. Here the infinitesimal charge dq is equal to sigma dA, that is infinitesimal charge in infinitesimal area dA. Now the electric field E vector due to the surface of total charge Q, what will be the total field due to all the infinitesimal charges? That is E vector is equal to 1 by 4 pi epsilon naught integral, instead of dq we have to write sigma dA by r square r unit. Then what will be E vector? E vector is equal to sigma by 4 pi epsilon naught dA by r square r unit. Here r is the distance between infinitesimal charge dq and the point P, and r unit is the direction pointing from dq towards P. Third one is volume charge distribution. Here the charge distribution is throughout the body. Here we are considering a sphere where the charges are distributed throughout the body, and the volume charge density is defined as the quantity of charge per unit volume. The variable is rho, given by rho is equal to Q by V. Q is the uniformly distributed charge in coulomb and V is the volume in meter cube. Then what will be the SI unit? Coulomb per meter cube, that is C m power minus 3. Here we consider a diagram of infinitesimal charge dq and the point P is at a distance of r. Pointing direction is r unit vector. Here dq is given by rho dV, that is infinitesimal charge in infinitesimal volume dV. Now the electric field E vector due to the volume of total charge q is given by E vector is equal to 1 by 4 pi epsilon naught integral rho dV by r square r unit, and E vector is equal to rho by 4 pi epsilon naught. Rho is a constant value, so rho by 4 pi epsilon naught integral dV by r square r unit, and r is the distance between infinitesimal charge dq and point P, and r unit direction from dq pointing towards P. Okay students, in this session we learned the continuous charge distribution as the first part, and in the second part we find the expression for E vector in terms of integration, and as the third part we discuss the three types of continuous charge distribution. I hope you all will be very clear in all the points. After you listen to the video, you take your note and recollect the points. It will be very helpful in your studies. Thank you.